Hi, today I'm going to introduce to you reparameterized policy learning for multimodal trajectory optimization. This is a joint work between UC San Diego and MIT IBM Watson AI Lab. Our method reparameterizes latent variables into multimodal policy to facilitate exploration and exploitation in continuous policy optimization. Our method outperforms existing methods on challenging object manipulation tasks that involve hard sparse reward exploration problems. This video briefly summarizes our approach to parameterizing learning policies in these challenging reinforcement learning tasks. We start by demonstrating the importance of multimodal parameterization. This is a one-dimensional continuous method, the most basic form of a continuous action-space reinforcement learning problem. The green curve is the reward. Despite its simplicity, it reveals core issues with current policy parameterization choices. One solution is to discretize the action space. Though it can find the best solution, it suffers from the inefficiency and inaccuracy for optimization. This is the commonly used Gaussian action parameterization. We discovered that, regardless of the initial standard deviation for the policy, the gradient with respect to mu is always positive, which pushes the entire probability density to the right. When the reward function isn't carefully engineered, like in this case, Gaussian policies optimized with reinforce tend to get stuck at the local optimum of the reward, even if it draws samples on the entire action space initially and find the global optimum with its samples. Our approach to policy parameterization constructs a generative model of optimal trajectories by introducing additional latent variables. The latent policy makes global adjustments to the action probability to maximize reward and entropy. The action policy makes local adjustments to the action probability to maximize reward, entropy, and its consistency with the latent variable. Combining the two results in the reparameterized policy gradient, or RPG for short. Optimizing using our method to convergence will bring the action probability to the actual global optimum of this reward function. Let's now dive deep into the heart of our methodology. We'll unpack key concepts like the reparameterized policy and its variational lower bound. In reinforcement learning, an agent samples actions from a policy to generate trajectories in a Markov decision process. The agent learns by maximizing the total future reward of the trajectory. The widely used Gaussian policy generates actions by adding random noises into the network's output, which limits the expressive power of the policy. Our reparameterized policy builds a more powerful policy class by introducing a latent variable z. Instead of adding noises into the network's output, it samples the random variable z first, and then the policy network conditions on this random variable z and reparameterizes it into the actions and future trajectories. We will look at this through the lens of the probabilistic graphical model. After simplification, we can view it as a generative model with two hidden variables and one observed variable. This enabled us to formulate the variational lower bound to infer the optimal trajectories. Like other generative models, we optimize our reparameterized policy using variational inference through a novel reformulation of the evidence lower bound. Like in the maximum entropy RL case, we can view the trajectory tau as the latent variable and the optimality O as the observed variable. Then we can maximize elbow to approximate the posterior of the optimal trajectories. Our method further includes the additional latent variable z besides the sample trajectories. The same equation holds for the two latent variables. We build an auxiliary encoder phi to map the sample trajectories back into the latent space. Optimizing the elbow concerning the encoder ensures the agent sample trajectories are in fact consistent with the latent variables, avoiding mode collapse. Optimizing elbow can then be formulated as a reinforcement learning problem with the original reward and the auxiliary terms. We can then use model-based reinforcement learning to solve it efficiently. We can learn a latent world model to assist with policy optimization. A novel object-centric intrinsic reward is introduced to encourage the agents to further maximize the entropy of the state visitation distribution. Our method, model-based RPG, can model the multimodal trajectory distribution, enabling a more efficient optimization and exploration. Now, let's look at some experiment results when applying our method to sequential decision-making tasks. We compare the exploration behavior by visualizing the trajectory distribution in a 2D maze navigation task, both optimizing only the intrinsic reward learned with random network distillation, or R&D. We found our method can explore the four modalities simultaneously, whereas the PPO agent have to go back and forth between the modes. We experimented with 6 sparse reward exploration tasks. The reward evaluates to 1 only upon task completion and evaluates to 0 everywhere else. We found that our method performs consistently even in tasks like stick pull, where all existing methods fail, even with the help of our novel object-centric R&D. The detailed performance results can be found in our paper. Here are some key takeaways from this video. First, we proposed a variational policy learning framework that models the posterior of multimodal optimal trajectories for reward maximization. Second, we demonstrated that a multimodal parameterization can help with escaping local optima and accelerating exploration in continuous policy optimization. Finally, when combined with a learned world model and a density estimator, our method, RPG, is able to solve these challenging sparse reward tasks with higher efficiency and reliability. Thank you for watching this video. Please make sure to check out our project webpage for more details, as well as our oral presentation at ICML 2023.